introduce Chelsi Sparti. Ms. Sparti holds a bachelor's degree in biology from Point Loma University and is pursuing a master's of energy and resources here at Cal. Her research looks at ways risk from energy system vulnerabilities can be mitigated by policy incentives in renewable technologies. In 2014, Ms. Sparti was a Fulbright Scholar in Malaysia. Later, she spent 4 years in Southern California at the Samuel Lawrence Foundation, where she focused on energy policy, including nuclear technology. In 2019, her work on radioactive waste at nuclear power plants was recognized by the California Senate President, Tony Atkins, with a Women's History Month Award. In 2020, she served on Congressman Mike Levin's task force to advance nuclear energy oversight. And in 2021, she was a fellow at the Clean Energy Leadership Institute. Please welcome Chelsi Sparti.
So I'm honored to be here today. I'm grateful to Professor Infelise for the invitation, and also wanted to acknowledge all of the people who have contributed to what I know and what I'm sharing with you here today. So this isn't just one person's knowledge. This is really based on decades of oral history, effort, and understanding. So today we're going to look at the nuclear fuel cycle, and we'll follow up in the next 2 sessions on other issues. So a little bit more about me. This is the cover of the task force report that the professor mentioned. And my undergrad is in biology. So my approach to this issue of radioactive waste, nuclear power, has to do with the study of life. It's not nuclear physics. I'm not approaching it as a purely policy lens. And so it's important to keep that in mind. My experiences on this issue are local, regional, state, and federal. So I'm happy to take any of your questions across those different angles. And these are my opinions, experiences, kind of professional background. It doesn't reflect on any of the groups that I've mentioned. And the beauty of how we've designed this is that there's going to be a panel with people who can answer the questions that I can't. So make sure that you're thinking of those tough questions, even if I can't answer them. This is the learning objective. And by the end of this, you'll be able to share with someone else what a nuclear fuel cycle is and why it's important that we're paying attention to all parts of it. Essentially, that's just before, during, and after a nuclear plant's operational life. One of the things I wanted to talk about is the expectations to make this fun, because if I'm just here talking, I'm going to get bored. It's not going to be fun for me, and it's probably not going to be fun for you. So I want to ask you to be brave, to speak up, raise your hands, engage, bring your unique perspectives, just like I'm bringing mine. And really just know that no one has this issue figured out. Not anyone you're going to hear from on the panel, not me for sure. This is really a work in progress of a topic. So feel comfortable in speaking up. Okay, so we'll start right now with that engagement. So I ask you to raise your hand if you've thought a lot about nuclear, any part of it. Okay, a couple of people. And if you've not spent any time thinking about nuclear at all. Couple more. Okay. Do you know someone that works in the nuclear industry? Just a few. If you have strong feelings about it one way or the other. Okay. And then if you've heard of high-level radioactive waste. Okay. A lot of hands went up on that one. So that's interesting for me. Usually people have not heard of that term. So this will be fun. Okay, so it's really important to identify what we're talking about. I've limited our focus because you could talk about an endless amount of things when it comes to this technology. So we're purely focused on nuclear fission. Within that, we're looking at operating reactors and the resulting waste that they create, which is high-level radioactive waste. We're looking at existing conventional US reactor technology. This is the stuff that is already being used. I'm not considering, in this specific lecture, we're not looking at things that are ideas, okay? We're going to touch on the science, the politics, and looking at the nuclear fuel cycle, looking at emerging legislative stuff, and ways that we have opportunities for improvements in our lifetime. This is the thing that motivates me, because there are things that we can do better. And I want to ask you, are there any other things that after the readings that you want to learn about? So we have a couple sessions to explore this. Yeah. The what?
Like the basics of nuclear energy, sort of like nuclear or that much background knowledge on it.
Yeah, I will talk about it. We could spend the whole time talking about it. So it's going to be very, very basic. But my goal is that this is the basics enough that will help you.
I'd love to hear your thoughts on some of these small scale reactors.
Mhm. Okay. We might be able to cover that in the next one. Okay.
I don't know whether this issue will be covered under the report. Maybe the strong relation between the science and the nuclear.
In the back.
I think France recently announced plans to look at nuclear.
Yeah, France is one of my favorites, so we'll get to that.
Maybe also for people like you who aren't so familiar, the most important laws and regulatory agencies involved in nuclear.
Sure. Any others? Yeah. Sure. That's the next session. Anyone else? Yeah.
This might fall into the kind of smaller scale nuclear reactors, but like on ships for shipping, like the green border.
Okay. And again, the fun thing is, I might not know these answers, but we've got a panel coming in a couple weeks. So thank you for engaging. Anyone else? Oh, we've got one. Sorry.
Yeah, I'd love to hear a little bit about the differences working at the local versus state and federal levels.
Okay. And then Nika, did you have a hand? No. Okay. So if anything else comes up, just let me know. This is how you're going to get the most out of this experience. I already know the stuff that I'm presenting. So, okay. So jumping right into the appeal of nuclear. Some of the things that are being talked about right now is that nuclear power is what's called baseload power. It's an emerging term that's coming up now as firm energy. So this means something that can be running 24/7. It's not intermittent like the wind or the sun. And so the expectation is that when you need energy, it's available. And it can fit into some of the gaps that we have because of renewables or because of other issues that happen in the world. That is a main argument for nuclear. Other issues are the social impact of having a lower carbon electricity generation like nuclear as opposed to coal. So people are definitely impacted by that. Perceived lower climate intensity of this fuel, and we'll talk about what that means. It's a fascinating technology. It's one of those things that you can spend a lifetime or many lifetimes learning about. Very highly paying jobs. This has been very attractive in past decades. It may not necessarily be the case going forward, depending on how nuclear shakes out. There's also a small amount of fuel that's required to produce a lot of energy for many years. And so that's appealing as opposed to fossil fuel plants where you're trucking it in constantly. Are there any other things that you've heard that are appealing about nuclear? Could be things that you think, could be things that other people think, could be things you read. Anyone? Okay, so this, not the greatest picture, but I wanted to be able to give you something. This is essentially how many of the reactors in the United States work. These are considered generation 2 reactors. And basically you have water, you have radioactive fuel, nuclear fuel, and you have a series of mechanical parts. The way that I've heard it explained by some of my mentors is that you're using the radioactive material to heat water to steam, using that steam to turn a turbine. It's a very complicated method for a simple way to generate energy. And that's something that we have to keep in mind. Is this whole process worth the outcome? Okay, is there any questions on this before we move forward? One of my gripes is that the water that they show doesn't look very realistic. You know, that's the key here. Without the water, this system doesn't work. So every nuclear plant has to be located, or the conventional ones, I should say, the ones that are in existence have to be located next to a body of water. Okay. So potential grid benefits. This is back to the baseload energy and the question about firm energy. So nuclear is contributing somewhere between 15 and 20% to the United States energy. Okay, so that's a decent amount. And the question of who's benefiting and where is really important when we're thinking about this. So here's a look over time. This is from the reading with Amory Lovins. Over time of the different energy that we've had in the United States. As you can see, renewables have steeply risen. Nuclear has stayed fairly steady. Here's another set of charts. And something that I think is really important when you're looking at these, as you may encounter them in your work for a variety of reasons. When you take a passing glance at this, it looks like nuclear is increasing in the chart that is on your left. It's not. It's staying steady, but the stuff beneath it is rising. The stuff beneath it is renewables. So the nuclear has stayed steady. That's why it's important to look at different images and understand the data you're looking at and not just sort of take the first instinct that you see. This is more of where I stand from the science perspective, getting involved in these types of things. Now back to the question of where and who benefits from nuclear. This is a map of the nuclear plants. It was really hard to find a map of all of the plants, both the ones that are operating and the ones that are decommissioning. Decommissioning means they're taking it apart. It's no longer creating electricity. What strikes you about this map? Yeah, go ahead.
There are a lot of reactors by the coast.
Okay, a lot of reactors by the coast. Empty in the middle. There's not much in the plains of the US. What?
There seems to be a concentration of sites, I would say, east and west.
Yep, definitely more nuclear plants in the Northeast and in upper Midwest. Most of these plants are located near cities as well, for the most part. They're somewhat near a population. But these are key aspects of the conversation about nuclear, because if you'll notice, the two locations that have been proposed for what's called consolidated interim storage, temporary storage, they're in New Mexico and Texas. New Mexico and Texas don't have many nuclear plants near them. So you'd be shipping waste from other places to these central locations. Same thing goes for Nevada. Nevada was proposed for the permanent disposal site of the nation's radioactive waste. They don't have a nuclear power plant. From a social perspective, from an environmental justice perspective, these are key things to be thinking about spatially. Some perspectives from the other side, the opposition. So some of the issues are that there's been coercion of indigenous peoples. I myself am a European and also California native, the Wintu tribe in Northern California. And What this means is that there's been coercion to mine uranium on indigenous lands, to use and test nuclear weapons on indigenous lands, and also to store radioactive material for an indeterminate amount of time on indigenous lands. So there's a long history there from perspective of environmental justice. The harm to natural resources, we've talked about water. There's also issues with land, air, and a variety of other kind of in the weeds topics as they relate to natural resources. There's high costs, as you read in the Amory Lovins piece. Can be time delays for construction, as well as with the long-term storage. There's the resulting toxic pollution. I often prefer to use the word pollution because waste doesn't really give you a visual image, but pollution does. And what's left over really is a type of pollution more than it is just simply waste. Uranium fuel, there's a lot of opposition because uranium fuel is finite with about 200 years left of reserves by some accounts. Depends on which numbers you use and how much of it is actually accessible. So this is not a renewable fuel. The other conversation is something we won't touch as much on, which is governance issues. This comes up internationally. Are there strong enough governance structures in place to protect the material that is used in the reactors that will then be stored somewhere? Or will that material turn into nuclear weapons? Any other comments on opposition?
Is water being used by the plant that is located not adjacent to those?
That's a great question. And we will have to ask our panelists because I'm not sure. I know that rivers can be used, lakes can be used. Obviously, the ocean is used in a lot of places. But in terms of groundwater, if they're digging down, that's something that I don't know.
Compared to usual hydropower plants, does it require less water?
Also a good question. And we will have to ask Greg, hydropower comparison. What I do know is that these plants are constantly flushing water in and out, and the water is heated as they're cooling the nuclear fuel. So they're bringing it in cool, sending it out very hot. How much it's using, I'm not sure. Any other questions? Okay, any other thoughts on the opposition that you've heard, that you're curious about or skeptical about? Yeah.
I mean, it strikes me as public fears about safety. Chernobyl, et cetera.
Yes. Yes, absolutely. So people's experience, they're seeing it in the media has changed a lot of perspectives. Yes.
Going off of that, I'm from the area next to a Rocketime accident,
Mhm.
and there's such fire cancer.
Right.
And I know that a lot of people in my community growing up brought a lot of, they asked for a lot of studies to be done, and after the studies have come out, it's just shown that with the rate of cancer and everything that are correlated, that is directly caused, is really, really high, so.
And Rocketime, is that Santa Susana?
Yeah, it's in the area.
Okay. Yeah, and I didn't mention this at the beginning, but I imagine that others of you have had experience in nuclear. If you need to take a break, drink water, whatever. It's a tough subject. In the back?
I think it's something that nuclear power will never.
And that's why people are opposed to it? Because it could, sorry, I couldn't hear you, because
When
it,
you hear about nuclear power, they think about the use of nuclear.
right, okay. They're connecting the two in their minds. Yeah, absolutely. The costs and the delays are intertwined. Very good. So some of the things we'll talk about today are, like I said, the fuel cycle, climate impacts and how that's affecting nuclear plants and the resulting radioactive waste, containment issues, which is squarely in the work that I did previously, and recent actions in various legislatures. So fuel cycle, again, this is the before, during, and after with nuclear plants. And I think it's really important to understand because in the typical discourse, we're talking about the operation of nuclear power plants. Very rarely is the media, politicians, celebrities and other figures, rarely are they talking about the other stuff. And the other stuff is actually really important. So if you look at this, this is from the regulator, the federal regulator, the Nuclear Regulatory Commission. You'll notice that several of the arrows are at the beginning and at the end. Again, those are the parts that I think are important. Mining, milling, refining, enriching that leads towards fuel. That fuel, as you go into the blue and the green, can be used in the reactor and then goes into some sort of disposal. Now, this image is misleading on at least two accounts. One, that yellow arrow that says reprocessed uranium, might as well erase that whole thing because that no longer happens in the United States due to presidential action, I believe, by President Jimmy Carter, who prevented that reprocessing from happening in the United States. Reprocessing is essentially recycling the waste. Someone mentioned France earlier. France does this. And so essentially they can get more out of their nuclear material by sending it back through a reactor after they had done some processing to it. The United States doesn't. So that means we operate as a once through, and then we store material that still has a high potential to create energy, making it a somewhat inefficient process. You have a question? It is more expensive, but reprocessing can lead to issues that could potentially offer opportunities for weapons creation and corruption, collusion, other things. And so for that reason, the United States said, we're not even going to get near that in a way that could lead to that. Other questions?
I'm just interested, I guess, knowing how reprocessing might be different from my understanding is it goes back into the cycle almost as, not as if it's been mined, probably with additional steps, but it goes back into this enrichment. And so I guess the question I have is like, is there not concern that during the enrichment that there could be this like nuclear weapon, but only for reprocessing? That's why.
Okay, that's a good question for the folks that'll come back and talk to us. Any other questions? Okay, so with this, I just want you to be able to have a visual that there's a lot of steps involved. It's complicated. The second item that I wanted to say is that there is no disposal site, and we'll get to that later. But those arrows at the end are going nowhere. And so where is the radioactive waste from nuclear power that we've been generating for about 60 years? It's at all of the reactor sites. So the nuclear power plants produce the energy, and the waste is just placed there as essentially like a holding tank. We don't have anywhere else for it to go, so we're going to create a structure at the reactor, and we will wait. Not quite sure why these flowcharts haven't been updated. Maybe it's just easier to leave them this way, but that's the situation. Okay. So high-level radioactive waste. Many of you said you had heard of it before, so that's great for me. What is it? It's made of several different long-lived radionuclides. Long-lived, and when you're thinking about long-lived, you should think of extra long-lived in the range of thousands of years to hundreds of thousands of years. What I mentioned earlier about reprocessing is that spent fuel in the United States, again, we're only using 1% to 3% of the radioactive materials fissionable uranium. That means that it's a very inefficient process because there's 90 some odd % that could still produce energy. And in the United States, we say, not going to happen because we're not going to reprocess. Does that make sense? Okay. No, you're not understanding. So what that means is that you're only using 1% to 3% of the potential of that material to produce energy.
It just doesn't make sense.
Yeah, yes. It's necessary to isolate this material from all life. But the problem is that this material, if it does come out to the air, the land, the water, like in Chernobyl, Fukushima, or 3 Mile Island, or any of Rocketdyne, or any of the other locations where there's been accidents, is that it accumulates in plants, it accumulates in people, it accumulates in any other thing that's living. And it's a cumulative process that means that if you're exposed at Chernobyl, then you're exposed at Fukushima, then you're exposed at Rocketdyne, maybe you're a worker in the nuclear industry. Those effects and those harms stay in your body. And so there's physicians that measure these things, and it just is really important to understand that this bioaccumulates. In San Diego, where I worked, this happens in kelp, happens in fish, happens in the sand itself. Not necessarily the water, because the water is the ocean circulates a lot, so the material gets diluted. But there is a real issue with bioaccumulation. Yeah.
I don't really get it. So what's the US not using spent fuel?
The United States decided that it was too risky, that it could lead to people with bad intentions stealing the waste and using it for another purpose, selling it to another country. And so they said, we're just not even going to build the facilities. We're not going to allow it to happen. We're going to do one step in this process, and then we'll just leave it. And that was a big decision. I think that our panelists can talk more about it and talk more about any conversations to change that, repeal that, which I know is part of the nuclear discourse. But that's pretty much what it is about, governance issue.
I would love to learn more about how drugs is bioreactors.
Uh-huh. Okay. Okay, so the reaction. This is very basic, but what is going on? I mentioned earlier that you have water, you have all these containment structures, machinery, and you have the radioactive material. What's essentially going on is that a subatomic particle, which means it's something smaller than an atom, a neutron, is bumping into an atom. The atom is splitting. And when that split happens, a large amount of energy is released. And you're repeating this over and over and over again. That then creates heat, heats up the water. That steam that's produced from the water turns a turbine. From a reaction standpoint, these reactions can be controlled. If you have what's called a control rod and you insert the control rod into the other rods, you could think of it as sort of metal holding radioactive pellets. It's too much information for you, but you can get the idea that it's basically a 18-foot tall square thing with a bunch of radioactive pellets inside, encased in different materials, okay? They're creating this reaction. When they want it to stop, they put another metal, steel javelin, or you could think of it as like a big square, stops the reaction, okay? That's well understood by physicists. That's really just a basic understanding of what's going on. If you have more questions, go ahead.
There's also this concept of fusion power.
Yeah.
Which is similar, and it's like experimental and a big Chinese experiment. How is it different?
Fusion is very exciting, and it is very different. But I think that if I were to try to explain it right now, it would cause more confusion than I may have already caused. So if that's important to all of you, maybe we can ask that at the panel. Does that sound good? Head shakes yes, if you are interested in that. Okay, yes.
Can I just respond to that for just a moment?
Yeah.
Fusion would be a lot less dangerous than the fission reaction that is used in traditional nuclear power plants. Really big breakthrough, maybe 5 years ago. They got fusion in a laboratory to continue for 1.8 seconds. And that was a massive improvement from what they got before. So you see that we have a long ways to go before we're going to be using fusion.
Okay, so from a fission standpoint, it's a simple reaction that scientists know how to control as long as other things don't go wrong. And we'll talk about some of the other things that can go wrong.
Yeah, maybe you're gonna touch on this, but are we splitting uranium atoms? Are we using uranium to split water atoms? Maybe it's too much in the weeds.
No, it's the radioactive fuel that is interacting with itself. And the fuel itself has a mixture of a variety of radionuclides. Yeah, so the water is just there for cooling and to create the steam for the most part. Okay. What does it take to manage it? We've talked a little bit about that. It takes highly skilled labor. It takes strong process and procedures. It takes strong governance and regulation. It takes all the materials and the natural resources that we've mentioned as well. And it takes time. Okay, so this is the number of years in general that radioactive material, high-level radioactive waste from nuclear power plants in the US remains toxic to life. And that's a shocking number, right? Yeah. I mean, I was shocked when I learned this. Civilization wasn't even wearing clothes that many years ago. So we have a situation that we really don't know what's going to happen in this many years. And the reason it's this number, this high, and likely even higher into the millions of years, is because of the half-life of some of the materials that is in that waste, namely plutonium. So you have a very high number and not a whole lot of options of what to do about the waste. I wanted to quickly demonstrate and give you some visuals on what it looks like when you're doing these mines. So this is a mine in Australia. In the United States, uranium mining has been centered in Southwest states, mostly on the typical easier lands, federal lands and tribal lands. This is an open pit mine. What happens is when you go in and you extract for the uranium, you're not having a cleanup, any major remediation. You end up with land that looks like this. For obvious reasons, this causes problems, namely to water. If there's no remediation, if there's no knowledge on how to remediate this, you end up with large swaths of land, communities, societies that can no longer live there. And that's very disruptive. This is something to think about. It's a part of the story that doesn't often get told. Here's the areas where uranium has been mined in red in the United States. In pink are other potentials that have not been explored.
But in its natural state, is it not toxic? So it only becomes toxic once it's processed.
In its natural state, it's not accessible either. So the toxicity, I always err on the side of caution. So I'm writing your questions down because I'd rather you get an answer that is absolutely steadfast.
If it exists naturally, then would it very found?
That thinking, I think, lacks some of the reality. And the reason why is that this situation here is not a natural state. Pit mining, not natural at all. If you were to put the waste there and cover it up and say, going back to the normal state, it's not good enough because you've changed it in a chemical way. You've added things to it. Yeah, and I think that that's a great question to ask Greg in particular, who will be with us in 2 weeks. But this is one of the things to think about, that once you take it out and you use it, it's different. Kate.
I'm sorry if I missed this, but I'm curious about this mining. It sounds like what's happening to the uranium isn't happening yet. It's just the mining stage. So why does this land become, other than like the obvious like destruction of the land to make it look like this?
Yeah.
Why did it become unstable?
So like most extractive processes, it's not benign. You're going in with heavy machinery that is, think huge tractors, cranes, things that are big enough to make this impact on Earth. Highly toxic GHG greenhouse gas issues. You have chemicals that are being used in the extraction process. There's a lot going on that isn't just shovel and hammer. Lynn?
Really clear and a good picture, but I think that when the work is being done, there's a lot of critical
Absolutely. It's hard to live in, especially if you're someone that already has respiratory issues. And it can cause respiratory issues. So there's definitely a health aspect that comes in at this stage. Okay, so we've seen the mines. We might notice that a lot of the mines are also in the same area where there's not nuclear plants. And yeah.
What is the red and the pink?
So the red is where there's already been mining in the United States. And then the pink are areas that have been identified as potential uranium mines, but that have not been explored. So again, there's some patterns that are showing up in these issues spatially. I already mentioned this, but this is one of the groups that is in opposition, Indigenous folks that are from the Dene Nation, the Navajo Nation. And their sign is small, but what it says is no waste, no mining, no weapons. And something that's important to think about is these communities have been affected by all of those things. It's not just one, it's the whole piece of this process that has affected them. Again, New Mexico is one of the shortlisted locations for consolidated interim storage, which is a short-term nuclear waste storage for the nation. And the folks in this group consider this issue to be nuclear colonialism, forceful, part of the patriarchy, an issue that takes power away from people, land away from people, resources away. And it's something that's happened for generations. Does anyone know, changing the subject a little, does anyone know who won the Nobel Peace Prize in 2017? So it was a group in Europe called ICAN. And I believe that's International Committee for the Abolishing of Nuclear Weapons. And they won it and took it as an opportunity to create more organizing in the space. But I mentioned that to say that this issue is something that's gotten to be of national, international exposure. And their work in 2019 led to the introduction and later the ratifying of a ban on nuclear weapons, which went into effect, was ratified this time last year. Unsurprisingly, the US and other nuclear powers of the world did not sign on. It's other countries that are likely to be affected by it that are signing on to the ban on nuclear weapons. So someone asked about the regulatory climate. The Nuclear Regulatory Commission, NRC, at the federal level regulates everything that has to do with civilian nuclear power. I mention that because there's just like things in the international sphere are different than what happens in the US. Things that happen in the military and research labs are different than what happens at civilian nuclear power plants. The NRC preempts pretty much everyone else when it comes to nuclear power and radioactive waste. Maybe in the next session, we'll be able to spend more time on federal preemption, but that's a key issue when it comes to nuclear. What happens when it gets to the courts? I can share anecdotally that the court cases that I've seen are not often successful for those who are fighting issues dealing with nuclear power and radioactive waste, largely because judges defer back to the Nuclear Regulatory Commission. So not much changes, and it's really challenging to attempt any change. And someone else asked about court cases, and I'm happy to look it up and maybe get some help from Professor Infelise to do so. So climate impacts. Here are some of those resources that it takes to run a nuclear power plant. Water to cool it, the uranium, land, money, political resources, connections and things of that sort, time, water for cooling and enough water that can evaporate because you're experiencing a lot of evaporation from the heat and from the steam. Various construction materials, the storage infrastructure, and then the ongoing skilled labor. One of the things that's really interesting for a climate consideration is that the Union of Concerned Scientists has come out and talked about drought. Drought and hot water temperatures, perhaps in a lake or a river. Why might that be a problem for nuclear plants?
We need to spend more energy cooling the water before they get into the system.
That's a good point. They might need to spend more energy, but they don't. They choose not to. It's too hard. So what happens if the water is too hot or if there's no water in the river? The nuclear plant turns off. And this is an area that has not had much study. Someone in France did study it recently, and that article caught my eye. But the conversation may change in coming years about nuclear being a baseload power, a firm energy source. Because if the water is too hot or not there, the plant has to turn off. And that becomes very similar to renewable energy, like wind and solar.
Sorry, could you explain why the plant has to turn off?
Right. So the nuclear fuel is really hot and it needs cold water to cool it off. If you have hot water or warm water, let's say in the lake, and if you have hot fuel, the warmer water doesn't have the same ability to cool the fuel. And if the fuel doesn't get cool enough in a certain amount of time, you could have an accident. So it's not worth the risk of how many degrees or how many tenths of a degree. They say, no way, we're not going to risk it. We turn the plant off. And what we're seeing with climate change is warmer temperatures, hotter weather, more unpredictable events, and that this has been a problem in some places, namely in France, which is why they're studying it. Any other questions? Okay, other recent disasters. This is something that is closely related to my research and is something that when I worked in this space for the last 5 years that I paid close attention to. So flooding in Nebraska, that's where this picture is from, has caused this issue to happen quite frequently, every few years or perhaps more often now. What happens is that the water reaches the doors of the nuclear plant. And I know the picture is kind of small, but the water from the Missouri River has flooded everything in this picture. What happens when water gets into the building near the electrical equipment that controls the nuclear power plant is that it could lead to disaster. So this is a very troubling thing that happens in the United States. And what's more troubling is that the workers can't get around the river either. So in some cases, workers have to drive 3 hours to reach the plant for work. In the case of an accident, this would be a big issue because the workers can't get there fast enough. I don't know why they don't try to use a kayak or something. Maybe the water's too rapid, but this is an issue and they don't have a solution in the immediate term. Another thing is hurricanes in Florida. Whenever hurricanes go by the plants, which they do somewhat frequently, they have to turn off the plants. Same thing with wildfires in California, whether it's an active plant or the radioactive waste. These disasters can cause problems for the radioactive waste storage as they can cause problems for the operating plant. There was also a tornado that barely missed the plant in Maryland. And the question is, back to the hot water, back to all of these other things that are happening in the world with climate change, what does the future hold for nuclear plants in the United States? How will they be affected as things shift with weather patterns? One of the other things, this is San Onofre, halfway between Los Angeles and San Diego. This is the plant that I specifically, where my work focused. And the issue facing this plant is sea level rise in particular. Also tsunamis. Geologic study of the cliffs in this area show a long history of tsunamis over the years. The red arrows pointing to the radioactive waste storage. that means that sorry? That means that
This is just an amazing photo. I mean, clearly, if we had known, if we knew back then what we know today, we wouldn't have designed it that way, but this is clearly a disaster waiting to happen that needs to be managed.
right, and it is a disaster waiting to happen. It's 100 feet from the waves. Regularly, the high tide, which you can see right here, splashes up at the seawall. Another issue is that this, well, I'll get to that later, but these type of images are things that have attracted national news. And late last year, MSNBC covered this story, and a lawsuit that the foundation that I worked with were putting forward for the public interest case. But I really want you to understand that this arrow pointing to the storage, and then the thing behind that is also another storage facility. This decision was made by the utility. The Nuclear Regulatory Commission approved the license, but the utility got to make the decision. And they chose this spot. Somewhat peculiar decision because they had another plot of land that was across the freeway, which is Interstate 5, and they chose not to put it there. They wanted to give it back to their neighbors to the east, which is a Marine base, Camp Pendleton, one of the most important Marine bases to the United States military and our national security. Their land is what this nuclear plant is on. What I wanted to demonstrate with this picture is that you have the military base to the east, Interstate 5, the Amtrak Railway, and the ocean. It's pretty much bounded. And our concern here about national security is that there have been threats and there have been attempts on this particular nuclear power plant. It's within about 50 miles to the City Hall of San Diego. And it's just above 50 miles to the City Hall of Los Angeles. All of these problems at one plant, and there are so many more in the United States. From a national security perspective, this goes back to some of the governance questions that we had. These types of plants are in other countries of the world that don't have a strong governance. So I'll leave you with that thought about how we've gotten here from 1960s to now. Mid-1960s. Yeah, so there was a lot of hope at that point around nuclear. Some of you may have heard about too cheap to meter. The people that were involved with nuclear in the early days believed that it would be a very cheap source of electricity, and it didn't pan out that way. It's actually one of or the most expensive forms of electricity, and I will have more time to talk about that in the next session. Okay, so containment. Again, we're looking at storage of radioactive waste and power plants across 30 states. There's 65 plants. Some of them have more than one reactor. And that equates to about 90,000 metric tons of radioactive waste and growing. As we produce more nuclear power, we're producing more radioactive waste. These numbers are so big that it's hard to even conceptualize what that means. This is a huge amount of toxic material, and there's no disposal site. There's no plan. There's nothing. I gave you this longer version from some of my colleagues, the Alleys. Bill Alley was the director of a portion of the project with the USGS, the US Geological Survey, who studied Yucca Mountain. Bill and his wife, Rose, went on to write this book that is both harrowing, but also they have as much humor as you could pack into something of this sort. What I want to hit home with this adapted version is that we've been working on this for well over 40 years in terms of finding a place to dispose of the waste. And what we end up with is a lot of money spent, and some would say a lot of years wasted. This says in 2008, there was 25 years of study on Yucca Mountain in Nevada and $10 billion spent. As of today, it's over $16 billion spent and something we can't use. It was closed down mostly due to political pressure. There were some scientific issues found, but they exceeded the realm of 10,000 years. So in 10,000 years or beyond, we would be worried. But Yucca Mountain, according to the experts that worked on the project, believed that geologically, the material stored from the nation and disposed of in Yucca Mountain could be isolated from the groundwater. That's the real concern. It could be isolated from the groundwater for at least 10,000 years. Does that make sense? That's an important part to understand, because you'll hear the science was X, Y, and Z. The politics was X, Y, and Z. Well, we had a plan for 10,000 years and we threw it away as a country. And that happened very recently. The other thing that I want to really hit home is that this is a contemporary issue. This isn't the issue for your grandparents or your parents. This is an issue happening in our lifetime, and there are solutions that we can implement in our lifetime. And one of those solutions is the task force report that I was part of. Our goal with the task force report was to shift the focus from trying to figure out, do we do temporary storage? Do we do permanent storage? What do we do? As a country, we're just arguing for decades and decades about this. So what we said is, we're not thinking about what happens to the waste at the nuclear power plants. We see that we do not have a disposal site. So instead of arguing about that, let's make sure that we could contain the waste at nuclear power plant sites until there's a place we can move it to. That sort of common sense logic is not something that the utilities are thinking of. It's not something the Nuclear Regulatory Commission is thinking of. And our task force group really started shifting this perspective. The findings that we focused on was how to make sure that the waste is safe, how to make sure that we have a way to understand when a problem happens, to detect a problem in the canisters that are holding the radioactive material. How do we deal with that problem on site at the nuclear power plant? And how do we make sure that we meet all of the federal regulations to allow it to be moved off site? Now, I included a piece of those regulations, something that I've committed to memory because I've used it so often. The problem is that the Department of Energy will not take title to the waste if the storage canisters are destroyed or damaged in any way. That makes sense. Does the utility plan for that? We were thinking about those questions. We were thinking about the questions of how would a utility in the United States clean up an accident? How are they finding the problems? And to understand that, I want to show you the spent fuel pool. So at a nuclear plant, the picture I showed you at the beginning was the operating reactor portion of the plant. When material is no longer being used for the electricity producing reaction, those rods are removed and those fuel assemblies are put in what's called a spent fuel pool. This is the place where they go to cool off for somewhere between 5 and 10 years, depending on the type of fuel. Okay. This is where the water is going in and out, cooling for 5 to 10 years. One thing that I'll plant in your minds is that cyber attacks have targeted pools like this, because if you turn off the electricity to the pool that pumps the water, you turn off the water. If you turn off the water, you have a meltdown. You have a nuclear accident. There's a great article in the New York Times, and I can add that to recommended readings, additional readings. But basically, In this way, the spent fuel pools are a large target. The waste is here for 5 to 10 years, as I mentioned. Then from here, it gets, the water shields a type of the radiation. The canisters that are used to store the waste are submerged. And not the greatest picture, but the best one I can find. That long thing is the fuel assembly that holds the radioactive material. They take that and they put it into the canister, which is what you see at the bottom. Essentially just a circle with a metal rack. Okay, this is roughly after 10 years, they put it into this. They have a way to, in the United States, we use these type of canisters that are welded shut at most of the sites. Put everything in, get a way to get all the water out. There's a process to add an inert gas like helium. So there's only gas around it. They weld it, take it out, and put it away onto a facility that's on site. At the very basic level, you should understand that there's radioactive material that does a reaction. At some point, that material can no longer be used according to the specifications of the plant. It's put into a pool to cool. It's put into a canister without any water in it. And that canister passively cools forever. I want to show you these canisters. So the one on the left is a whole text canister that's used at many United States sites. It's used at San Onofre, the site that I focused a lot of my work on. It holds 37 fuel assemblies. So it's very densely packed. The canister itself is 5/8 of an inch thick steel. That's less than 1 inch. That's the thickness of plywood. What you see on the right is a German castor cask. In the advocacy field that I worked in, we often use canister for the thinner canisters, the one on the left, cask for the thicker storage casks. Now, what you see is for the German cask is it holds 21 fuel assemblies, so it's less dense. It's made of cast iron covered in epoxy, and it has a lid that's bolted that you could open if you need to. One of the reasons they do this is because they reprocess. They want that option to reprocess. They want the option to go in and check on the fuel. United States, we weld shut, which means we're not opening it unless we're destroying the canister. Okay. This is important because the utility chooses this. So the utilities in the United States are going for a few things. I've boiled it down to cost. You can buy less of the canisters that are on the left because your waste is densely packed. Time, because you can load the fuel faster in the canister on the left because it has more ability to cool through a thinner steel wall. And space, because you can fit a greater number of these canisters on a smaller piece of land. Now I'm going to take you through, this is at San Onofre, the site that's near Los Angeles and San Diego, and I'm going to show you what it looks like on the inside of this. These are the steel silos that the canisters go into. This is before the concrete is added on the outside. I want to give you an idea of what it looks like. This is the thing that the canister drops down into. There's some weld marks on the outside. They're 18 feet tall. Look kind of strange, but they're on ground. They're not buried. What is created is this. So all of those things, which I'll call a silo, are covered in concrete and rhubarb and other things to create some stability in an earthquake zone. At this site in particular, same one I showed you before, there's 4 earthquake faults. Some of them are onshore, which means on land. Some of them are offshore in the ocean. That's problematic. So you can see the semi below grade. They access it. Thing on the left is a crane. That crane can roll up, go over. It holds a canister, goes over one of those holes, drops the canister down. And we don't have time to talk about the science, but if anyone's interested, I can explain some of the things we found in the task force report. But what's really important to notice with this is that there's no way to visualize the canister. You can't see it, you can't walk by it. You don't know if something's going on with it. You can't even measure it. You can't measure the temperature. You can't do anything, which means we can't use the knowledge of Europe and what they've done. Something that's somewhat damning is that this is the same design of a storage facility that is being proposed for consolidated interim storage, that short-term temporary storage in New Mexico or Texas. Some of the questions I asked as a task force member was, how many of these exist? Basic question. And I asked my colleague who worked in the nuclear industry. He said, I'll look it up. I don't know. And he looked it up, and the answer is 2. There are 2 of these facilities in the US. One of them is at San Onofre. This one you've seen. The other one is in Missouri. It's not a great picture. I guess they don't pay a videographer to be on staff like they do at San Onofre. But as you can notice, this one looks kind of rudimentary, looks kind of basic. It doesn't look quite as involved as this one. This one at San Onofre is also twice as large. And so our country is making a big gamble on these 2 sites. I would venture to say that the San Onofre site is somewhat of a guinea pig, given that it's the only site that's near water. Water, especially ocean water, it causes corrosion with the salts in the water. And that advances problems on the canisters like cracking in the steel. One of the things that I do need to mention is that there's no plan, in addition to not being able to visualize problems, there's no plan for repairing or replacing any of these canisters.
Do you have a picture of offshore storage?
There is no offshore storage. I'm talking about offshore fault lines of earthquakes. There was offshore storage of nuclear material at one time in the long history of nuclear weapons and other research, which is really fascinating, but people took drums of 55-gallon drums of radioactive material off the coast of California and other places, and the East Coast as well, and shot them so they would sink. And there's radioactive material contaminating various parts of the ocean. So yeah, but this is all on land.
In the long term, would it be safe when
I've heard these questions, launch it into space, launch it into the sun. People have studied it. I'll say that. I think that the problems of that going wrong would be pretty huge. So something to consider. So as you can see from this picture, the people in the advocacy space, the people in legislature started to think about what we thought about at the task force, which is why let's scale back. Let's think about the problem locally at the reactors before we jump ahead. San Onofre has a particular issue because it's this design I showed you. Now this is the inside of a silo. There's a ring, as you can see, and then there's these seismic restraints so that if shaking happens, it's not moving too much. This ring, there's not much space between it and the canister. It's only 1/4 of an inch clearance. That's a problem because you have to get the canister down without a whole lot of visibility. You can't be in the same space as that. Cameras aren't that effective at telling you where the canister is. 1/4 inch clearance. Some of the scientists I work with said, I think that we're running into some problems when you're putting the canisters down into these silos. And again, it's a new design. People may not have explored it. What we found is that there's scratches and gouging that's happening as the canisters are being downloaded. These are 50-ton canisters, 18 feet tall, pretty big. What happened in 2018 is that a canister got stuck on that ring, that shield ring, like this. No one noticed until they saw that the bands that were holding it were slack and the radiation readings were still high. So after almost an hour, somebody said, something's wrong. The canister, they lifted it back up and put it back down. Didn't inspect it, didn't check out what was going on, didn't check if it had been deformed. The metal had been deformed at the bottom. We don't know what's wrong with that canister. And then that was canister 4, and they kept loading. This is what came out the next year. This thing that looks like vomit is a type of carbon staining. And when I saw this, my stomach turned. After studying it for several years, this is the site of a canister at San Onofre. And what happened is that the carbon the carbon steel that they have inside of the silo versus the steel that is the canister had a reaction. Now that's not what you want to see. Neither is this. And the inspector that got these pictures reinforced that you're not supposed to have scratches on these canisters. They can't be stored that way. They're not certified to have scratches or gouges. And so like none of these even look the same. The utility had to come and reckon with the fact that they don't know how to deal with this and they didn't expect it. Neither did the regulatory agency for that matter. Everyone said this wouldn't happen. So going through all this rudimentary stuff, the stuff that exists here in the United States, I want to quickly touch on, we don't have very many minutes left, 5 minutes. So I want to quickly touch on what it looks like in other places. This is Finland, a place called Onkalo. Onkalo is not many people live on this island. It's almost uninhabited. It's a forest, it's off the coast. And they've designed this permanent disposal inside of the rock, about a quarter of a mile down. And each of these lines is a place where they would put a canister. So this, we can agree that this looks a lot better than what we've got going on in the temporary storage of the US, right? Each of these lines that you see, they put a canister, they separate it, and then they backfill it with clay. Now this clay is bentonite clay, and it just so happens that it's the same thing that's in kitty litter. If you read about the accident that recently happened several years ago in New Mexico at the WIPP station, WIPP, they had an issue with picking the wrong kitty litter and having an accident at that storage facility. But another thing I want you to understand is that these canisters aren't even located right next to each other. They've planned for redundancies. They've designed it. They've engineered it so that they can fix things if they go wrong. Not the case in the United States. Another thing to notice is that the canisters themselves in this picture have about 12 fuel assemblies. So they're much less densely packed. They're in copper canisters, similar, not the same, but similar to what Germany uses in other places of the world. So this is different. It's another reason why it's very difficult to compare France or Japan, Germany, Finland, Switzerland. Different places use different methods. They also use different nuclear technology. This is Switzerland. Now this is their temporary site. It's in a building, which means that you have the redundancy of dealing with something inside of a building if something goes wrong before it goes to the atmosphere. That's a person in the middle. And again, you'll notice these German style casks that are between 10 inches and 19 inches thick, as opposed to the 5/8 inch canisters that are used at San Onofre and other places in the US. So very quickly, some of the top line things that have happened from the task force. There's been over $500 million appropriated for research and development and other storage issues. Again, the task force report was published in 2020, so this is pretty fast moving. The Congressman Mike Levin and other members of Congress are motivated to do something. There was the creation recently of the Congressional Spent Fuel Caucus, which means that a bipartisan group of members of Congress are meeting regularly to talk about this issue. There's also several pieces of legislation that have been introduced, namely to restart the consent-based repository process for permanent disposal, which is a good thing. We want to see that happen. Other aspects based on all that I've shared with you is that there's conversations about having specifications on the lifespans of canisters. We didn't get to touch on this, but design life is a big issue in nuclear power. There's a design life of roughly 60 years for a nuclear power plant. Utilities try to extend that. There's a design life for the canisters at San Onofre of roughly 60 years, 60 years of storage. We're not really thinking as a country beyond 60 years if everything goes right. That doesn't account for scratches, gouges, corrosion, cracking, natural disaster. So we're really not counting the risk. Another thing that's happened is there's conversations about improving civilian coordination of nuclear power plants with military and learning how we could do better. You read the local policy, and really what I wanted to do with that is give you some exposure to the issues, how local communities in Southern California are approaching this issue, and sort of what's the gold standard and how to make things better. And what we end up with is the fact that there's more work to be done. We're going to get to have more conversations, so that's really nice. Your learning will be extended in that way. But really, there's a lot of things that we don't have figured out as a country, as a world. And what we need is more people who are willing to get involved and help solve this issue. And so we'll be able to share these slides with you. I'm happy to stick around a couple minutes and answer any other questions and get your other things you're interested in learning about. Thank you for sticking with it and appreciate the opportunity to come back and share more.